All right, and we're back. But again, the homework for section 2-4 is accurate on Canvas. So I know I don't have it correct on the board yet, but it's still there. But here's what I was going to say. So we've got this quiz coming up on Thursday. Okay, this is actually not accurate. I put it 2-1 to 2-4 quiz. That's actually going to be a 2-1 to 2-3 quiz. I did not mention that yesterday, and it looks deceiving on the board there. We are not going to. Nothing from this precise definition of a limit section is going to be on the quiz on Thursday. Okay, it's all from sections 2-1, 2-2, and 2-3, and honestly, mainly from 2-2 and 2-3. Okay, I didn't put any tangent line problems on there, or velocity problems on there. So it's really going to be from sections 2-2 and 2-3. Okay. Now, will sections 2-1 and 2-4 be on the chapter 2 test? Of course, but on this quiz on Thursday, it's just going to be from sections 2-2 and 2-3. Okay, that kind of ease your worries a little bit, maybe. All right, so let's get into it. Let's get after it. So yesterday, I kind of bored you guys to death. Man, I had to call out Luke Candle on the video. Luke Candle, I almost gave him toothpicks to keep his eyes open. I mean, he was falling asleep. Like, give me this. But I know you guys were all like with me, like interested, right? On the edge of your seats, so excited about this. So excited. Okay, but again, just to kind of recap what we talked about yesterday. What we are going to be doing here in this section is looking at how close is close enough. How close is sufficiently close? You know, we assume it's going to go to some number, but how do we mathematically state that? Because again, saying that it's going to get closer and closer to some value is a little bit too vague for mathematicians' purposes. Okay, so what we're going to use is this whole idea of the epsilon delta definition of a limit, right? We're saying that if we choose, and now this again is this curvy looking e, okay, is called epsilon. It's the lowercase epsilon, and if I look up epsilon here, just to show you epsilon, okay, the Greek letter epsilon, okay, that is that. Oh no, that's sigma. That's not epsilon. I thought it was Greek alphabet. Where's epsilon at? That's not caps, is it? Oh, that's why I don't recognize it. The capital letter epsilon is just a big capital E. So this is the lowercase version of epsilon. Delta, that's the lowercase version of delta. So these things, these letters are just variables. Okay? They're just placeholders. Don't let them confuse you. They're just placeholders. And what we're saying here is that we're going to find an acceptable error range. And that acceptable error range is going to be called epsilon. And we want to kind of, we're like taking target practice. And we're seeing, okay, what x values are going to get us on our target? What x values are going to let us be in our acceptable error range? And if we can find what values are going to make those y values happen, then we can find out our delta. And our delta is going to be the difference away our x has to be, you know? Like, so if we were trying to get closer and closer to our limit, and maybe our limit was going to x goes to 3, I think was the one that we were looking at yesterday. And we said, okay, what if we choose 2.9 or 2.99 or 2.999? What we're doing there is we're reducing our delta. Okay, when I make delta smaller and smaller and smaller, that's getting closer and closer to the x value that we're trying to look at. And our output values, what we plug and chug to, that is reducing our epsilon. Okay, so the closer and closer we want L to actually get to the value of our limit, or the value of our function, that's making epsilon closer and closer and closer, or making epsilon smaller and smaller and smaller. Thus, in turn, making delta smaller and smaller and smaller. And what we're doing here mathematically is saying that, well, instead of choosing 0.1, what we're going to do is just make it arbitrary. Because if you can make it arbitrary, you can make it anything you want. And if you can make it anything you want, you can make it as small as it can possibly ever be. And for mathematicians' sake, that's small enough. That's a reasonable definition of a limit. If we just make it arbitrary, then we can make it whatever we want. Okay. All right. And again, visually, this is what we're looking at here. We're looking at our acceptable range, and then we're kind of playing target practice with the x values. We're saying, okay, what x values are going to get us in that acceptable range, and that's going to be our delta. The smaller we make our epsilon, the smaller we have to make our delta. Okay. The closer we have to get to x to actually run it. All right, so let's get back to this problem. I'm just going to treat this problem from scratch. Okay, I'm going to treat this problem like I'm doing it from scratch, and I'm going to get my notes just so I don't screw anything up here. I made notes to myself. So try to make it a little bit clearer for you. All right, so this is the example that we started in on yesterday. Right? This is the example that we started in on yesterday. We say since f of x is equal to, or consider f of x being equal to x to the third minus 5x plus 6. And because it is polynomial, we were very, we're very good at just running the limit of a polynomial because all you need to do is just plug it in. So all I would need to do is say, okay, if I know the limit as x goes to 1 of f of x is going to be 2, how close do we need to get to 2? If I want to be within 0.2 of 2, how close do we have to make our x values? That's really this question. If I want to get within, I'm playing target practice in my acceptable range. My target is within 0.2 of 2. So I mean all the way up to 2.2 and all the way down below to 1.8. I need to figure out what x values hit my target. Okay? And again, I could give you problems where this is not there. Right? That statement you have to come up with. Okay? What do I mean by that? Well, I have to say the value of the function f of x minus the true limit has to be less than 0.2. Okay? That's our acceptable range. That's what we're looking at here. Well, we know the value of our function. The value of our function is just x to the third minus 5x plus 6 minus 2 is less than 0.2. Right? And we know from algebra that that's inequality, or absolute value inequality, and that's going to be a less than, right? Less than means an and inequality, an and compound inequality, where we have x to the third minus 5x plus 6 minus 2. I know we could simplify that if we wanted to, but I'm not going to right now because I'd like to visualize it this way. And on the left side, we have the negative version of that number, and on the right side, we have the positive version of that number. And the reason I'm not simplifying it because I think it's beneficial for us to see, okay, here is where we would add 2 for this compound inequality and saying, okay, 1.8 and 2.2. That's mathematically what I'm looking at here. Okay? I need to figure out where that's going to happen. The only way I know how to figure out where that's going to happen, because if this was quadratic, we could use the quadratic formula to solve each of these things. If this was linear, we could just solve them directly and figure out what it is. But because it's cubic, I have to go to my calculator. I'm kind of stuck with our calculator. So that's why in my calculator, I plugged in x to the third minus 5x plus 6, and we were looking at the top end of this thing. Okay. I am going to use the window that the book provided. This was, because this is a good window. The x values went from 1.7 to, oh shoot, what is that? 1.8 to 2. What x value made that happen? 1.12. Okay, so I'm going to go x minimum. Looks like it's 1.7. X maximum, let's say 2. Or 1.24. Oh, no. I'm sorry. I'm looking at the y values. That's why it's throwing me off. 0.8. Okay. To, let's go to 1.2. I'm just kind of ballparking. Ooh, Let's go to 1.2. And then my y minimum, I tried to play around with that, but it was unsuccessful. My y minimum, let's go 1.7 to 2.3. Why am I doing that? Why am I choosing that? Look, that's what the y values need to come out to be. Right? So now when I graph this, okay, that's the intersection point that I need to find. And I could go so far as to graph this other one as well. What if I wanted to do both of them, 1.8 and 2.2? Okay, there's my target practice, right? There's my acceptable range. I know this function that's probably some sort of cubic function. This is where I want to land within this range, right? I need to figure out the x values that land me within that range. Well, let's figure out what x values they are. Second, calculate the intersection point. First curve, enter. Let's go for the top one, enter. And then we'll put it somewhere close to that. Okay, 0.911. Ooh, 0.911. Okay, let's do the other intersection point. Second, calculate the other intersection point. First curve, enter. Second curve, I want to jump down to the bottom one. Guess somewhere over here. Well, it's going to find it. 1.12. Okay. So those are the x values that hit my targets. Okay. Those are the x values that hit my target. 0.911 and 1.12. Okay. 0.911 and 1.12. Now, that means, let me scroll down a little bit. Oh, can't. Oh, get back. Where's my extend page button? To do that, apparently. Okay, so that means our acceptable range for x is here. Yeah.
Yesterday when you did this problem, was it not the x?
I know. I think I used the other intersection point and I should not have. Yeah. Because this waves twice really closely, I think I calculated the wrong ones. That's why I wanted to redo this from scratch here. So those are the two x values that I have, 0.91 and 1.12. Okay, now, how close are those values from, now what did I want to make x go to? I wanted to make x go to 1. You follow me? I wanted to make x go to 1. Okay, how far away from 1 is 1.12? So this delta here would be equal to 0.12. You follow me? What would this delta be equal to for this one? 0.09, right? 0.09. You always want to go with the smaller delta. You always want to go with the smaller delta, and here's why. If I choose the delta to be 0.12, that will allow me to solve for x's on the other side all the way down to, well, 0.12 below 1, right? 0.88. And 0.88 is not okay. 0.88 will not land me in my acceptable range. It has to be 0.09. So I say this guy wins. My delta is 0.09. Okay. You always want to go with the smaller delta. And again, delta is always going to be the change from the x value that you find and the x value that you were trying to get to. Okay. All right. Everybody's favorite first word of a problem. Prove. I'll probably only ever put like one proof on the test. Because these are just tricky. I could have you find delta for any type of function. I mean, that's a very common question to ask. What's the delta that will land me within 0.1? What's the delta that land me within 0.11? Whatever it may be. And then you find that value of delta. Find the x value, then choose the smaller one to land me in my range. But the proofs can be a little bit different. So I've tried, this is my third year teaching this, I've tried to narrow down what the best way possible is to do this. So here's the simplest way I can explain it. There's two parts to these proofs. There's the prep, and then there's the actual statement of the proof. Okay? There's the prep, and then there's the actual statement of the proof. You know, for example, did I need to tell you what the limit was on this? Could you have evaluated that? I mean, that's pretty simple, right? 3 times 4 is 12, minus 5 is 7. I mean, that's a pretty simple limit, right? Okay, now, if I know what the limit is going to go to, I know that my A value is 3. I know that my L is 7, right? I know that A is 3 and L is 7. What I would like to say is that if the absolute value of x minus 3 is less than delta, right? I know that has to be true. Well, that means the difference away, the absolute value of f of x is to 7, has to be less than epsilon, right? That was like our formal definition of, our precise definition of a limit. The absolute value of x minus 3 is less than delta. The absolute value of f of x minus the true limit is epsilon, less than epsilon. Okay, let's start running the value here. 4x minus 5 minus 7 is less than epsilon. Reduce it. 4x, minus 12. I didn't actually reduce it. 4x minus 12 has to be less than epsilon. I can factor out a 4, right? Yes, you can actually factor it all the way to the outside. Okay, let's solve for the absolute value of x minus 3, and you'll see why here in a second. The absolute value of x minus 3 is less than epsilon over 4. Okay, basically what you're trying to do is figure out what to make your delta. What delta do you have to choose so that we become less than epsilon? What delta value do you have to choose so that you become less than epsilon, which is essentially the exact same thing that we did on the last problem. We were given epsilon, and we just had to say, well, what delta do we have to choose? Well, we had to go with the smaller value of the delta, that 0.09. So we say that I know the absolute value of x minus 3 has to be less than epsilon over 4. So what delta are we going to choose? Look at this statement and look at that statement. What is delta equal to? What is delta equal to? Epsilon over 4. So what we just showed here is that we are going to choose the delta value of epsilon over 4. Now, how did we do that? We took our output, our f of x minus L, and kind of manipulated it until we saw the difference between x and our a. Okay, let me say that again. How did we find this epsilon over 4? We took the output minus L, manipulated it until we came up with x minus a. Okay? So we found that delta is equal to epsilon over 4. That's our prep for the proof. So here's our formal definition of a proof. Okay? Here's our formal proof for this. We are given, as long as epsilon is greater than 0 and 0 is less than absolute value x minus 3 less than delta. Actually, we don't need this because it's never going to be less than 0. We are going to choose choose delta to be epsilon over 4. That's our first statement of the proof. We're given that epsilon is greater than 0. We're kind of like setting our boundaries. We're saying epsilon is greater than 0, and the absolute value of x minus 3 is going to be less than delta. We're going to choose delta to be epsilon over 4. And now what we're going to do is kind of like work it backward. We're going to work it backward. Okay. So we're going to say that, let me extend my page a little bit. We're going to say that the absolute value of 4x minus 5 minus 7 is going to be equivalent to, well, that's the absolute value of 4x minus 12, which is equivalent to 4 quantity, or absolute value, x minus 3, which is actually, I should say this. What is that less than? What is that less than? What is that less than? In terms of delta, is it actually just less than just straight up delta? Because absolute value of x minus 3 has to be less than delta. So what's it actually less than? 4 delta. See, look at this statement. You know, this isn't part of the proof, but what if I just did this? Isn't that an equivalent statement, multiplying each side by 4? So 4 absolute value of x minus 3 has to be less than 4 delta. But what did we choose to be delta? Epsilon over 4. So we can say that this is equivalent to saying 4, kind of a new statement here. We can say that 4 delta is equivalent to 4 times epsilon over 4, which is equivalent to epsilon. So therefore, we could say, so this statement combined with this statement is saying that this, which led us all the way to here, this beginning statement, so 4x minus 5 minus 7, which we saw was all the way equivalent or less than 4 delta, is now less than, because 4 delta is epsilon. And that's the end result of our proof. That's like our final statement of the proof. Because what did we want to show? We wanted to show that the difference between the output of the function and the true limit is going to be less than epsilon. That's the end result of the precise definition of a limit, right? That's what you want to show. You want to end the proof every time with the absolute value of the function minus L less than epsilon. Did we do that here? Yes. So therefore we know that the absolute value of 4x minus 5 minus 7, f of x minus L, has to be less than epsilon. Okay. We're only going to do one more of these, but I kind of want to recap this just to make sure we know each of the parts. So how did we start this? We started this by figuring out what we needed to choose as our delta. How did we do that? We said f of x minus 7 less than epsilon and just started doing some algebra until we found this piece. And then we could say, well, that's what we want as our delta. That's the prep. So now once we know what we have as our delta, now we start the proof. We set it up by saying, okay, we're going to choose epsilon to be greater than 0, and the absolute value of x minus 3 has to be less than delta. We're going to choose delta to be epsilon over 4. Now we start our proof. We say f of x minus 7 is equal to, and chain it all together until we get to 4 times our absolute value of x minus 3, which is 4 times our delta. See, we kind of have to look for this piece again. We have to get it to that x minus 3 piece again. And then we say, well, what can we multiply each side of this by to make it look like that? Oh, 4. So 4 absolute value of x minus 3 is less than 4 delta. So then I can chain these two statements together. This and the fact that for delta is actually epsilon. This has to be less than this. And that's the end statement. So the absolute value of 4x minus 7, or sorry, 4x minus 5 minus 7 is less than epsilon. Okay? Let's do one more of those. At some point yesterday during my 7th period, everybody just started laughing. Like, nobody knew what I was saying. I could have been speaking in German. Maybe it's Greek. It's Greek because I'm talking with the Greek letters, right? All right. Now, what I skipped over is just the fact that, and you don't need to write this down, the fact that you could do this with right hand and left hand limits. All these same rules apply. Everything follows with right hand and left hand limits. Okay, this is the only other one that we're going to do, because this is, once we get beyond this, like I did this my first year, and then I just kind of X'd it out. Don't do that anymore. It's bad. Use definition 4 to prove that, but honestly, we're just going to say, prove that the limit as x goes to 0 positively of square root of x is actually 0. Okay. Which makes sense, right? If I think about my square root function, as the closer and closer I get to 0 on my x, the closer and closer I get to 0 on my y. Okay, so here's my prep, right? I know that my a is 0 and my L is 0. Okay, so we know that this has to be less than epsilon, right? Okay, now, actually, you know what I can say? Is this ever going to come out negative because of the right-hand limit, right? And because the fact that my domain of the square root of x is always positive, right? So I can kind of take that off and then just say, okay, the square root of x has to be less than epsilon. Okay, so that means x is less than epsilon squared. Okay, now, what is my x minus a? Because that's what you have to look for, right? We were at like a, what was it, last problem? X minus 3. In this case, what's my x minus a? Well, what is x minus 0? 0. That's just x. Okay, so what delta am I going to choose this time? What's delta equivalent to in terms of epsilon? Epsilon squared. So delta is equal to, so you look at this statement and this statement. Delta is equal to epsilon squared. That's the first part. This is all just kind of our prep work so that we can say this. We have to figure out what epsilon, or what delta to choose in terms of epsilon. You know, this is, again, we know our target is epsilon. What x values am I going to have to be able to throw at it to make epsilon, to fall within to epsilon? Well, epsilon squared is equal to delta. Again, how did we get that? We took f of x minus L, set it less than epsilon. And the reason we were able to take off the opposite values is because, again, only positive numbers, right? I'm only looking at 0 from the right. I wouldn't be able to do this if this was a full limit because the limit does not exist from the other side. That being said, so that's why we can say the absolute value goes away. The square root of x, I can square to the opposite side, so x has to be less than epsilon squared. And we know, okay, take a look at your x minus a. I can do the same thing with my absolute values, but again, I'm only looking at it from the right, so I'm just taking them off right away. So x minus 0 is less than delta. which means x is less than delta. And then you look at these two statements and say, okay, well, that means that delta is equal to epsilon squared then. Okay, now let's start our proof. Okay, that's all just prep work. Here's our proof. Okay, we're given that epsilon is greater than 0. And that, see, look at our other proof. We want to say x minus 0 is less than delta. X minus 0 is less than delta. Or in other words, x is less than delta. So we're going to choose, we choose delta to be epsilon squared. Okay, so there's our setup. We're ready to go now. So we can say, then we know that the absolute value of x minus 0 is equal to the absolute value of x which is equal to just the square root of x, because it's always going to be positive. Now, take a look here. If I know x, if I have the square root of x here, if I know x is less than delta, okay, take a look at this statement. What if I square root both sides? So now we can say that's less than the square root of delta. Well, what is delta? Epsilon squared. So we can say, and delta, and since delta is equal to epsilon squared, that means the square root of delta is equal to the square root of epsilon squared, which is just epsilon. So what did we just say? We just said that this was less than, don't mistake that for an or equal to. This was less than this, which that, my friends, is the conclusion of the precise definition of a limit. Okay. So, you feel okay? A little bit. Kind of like this. Better than yesterday. That's good. Better than yesterday. All right. So, tomorrow I am going to kind of review some stuff about limits, okay, as well as answer any questions that you have over the homework, and then the homework will be due tomorrow night. That makes sense? Whatever time, I'm going to go through some limits, and I have some like problems pulled that I want to just do a couple more problems with you guys tomorrow in class, kind of like a little quiz review. And then whatever time remaining you will have to work on your section 2-4 homework, and then it'll be due that night. I know it's kind of a weird one because we have a quiz and it's kind of put in there too. So, but yeah. Questions about that? Yes.
Well, a lot of us healthcare people are not going to be here tomorrow.
Oh, I didn't even think about that. Who's that? Who's that mean? 1, 2, 3, 4, 5, 6. I'll be doing a video.
Yay.
What's tomorrow after Wednesday? I can stick around after school. Are you guys around after school? Or before school?
No. Yeah, we're leaving at 8:10, I think. Tomorrow.
Yeah, but we have to go to first period if we have one.
But then when do you guys get back?
Like end of the day.
End of the day?
I don't think so. Do we even get back?
Like, no, it's
No.
6:30.
I mean, I'll be around.
Okay.
Or I'll be around, I mean, Thursday before school too.
Okay.
Any questions?
Okay.
Sorry. The joys of being a well-rounded student. All right. Let me stop the video.